Okay, yeah. So, hi everyone. So, good afternoon all. So, first of all, let me know whether audio and video everything clear. Tell me here. So, if audio and video is not clear, please give some comment in chat box. Okay. Okay. Yeah. So let me know whether audio and video everything clear here, right? Alok Kumar, good afternoon Alok Kumar. Is audio and video clear, Alok Kumar? Yes? Okay. So I hope it is crystal clear, right? Okay. Yeah. So we are dealing with the subject electromagnetics, and the topic that we are dealing is nothing but magnetostatics. Right? Okay. Okay. Yeah. So in magnetostatics, we are dealing with a Lorentz force equation, right? We are dealing with Lorentz force equation. So we have seen that the Lorentz force equation for B field, is nothing but what here? F bar is equal to what? Q into V bar cross B bar, right? Next, Lorentz force equation for electric field is what here? Is F bar is equal to what? F bar is equal to E bar into Q. Okay. So if you are having both E and B fields, so in this case, F bar is equal to what? F bar is equal to, you can write Q into E bar plus what? Plus of V bar cross B bar. Yes or no? I have just added these two. Okay. So this is the Lorentz force equation for if you are having both electric field and magnetic field. So we have seen the applications here. Yes or no? We have seen the applications of this Lorentz force equation. So what is the first one we have seen here? So that is nothing but Hall effect. Understood? So here what we have seen? So we have taken a semiconductor. And here we have applied a potential difference V. So we have observed the current is flowing in this direction, right? We have considered this as A and this as B. Okay. So this is extrinsic semiconductor. It may be what? It may be P type or N type. So we have to determine whether it is P type or N type. So what we have done? We have assumed here. We have assumed initially it as what? It as P type semiconductor. If it is a P type semiconductor, the charge carriers are nothing but positive charge carriers. The majority charge carriers are nothing but positive charge carriers. So plus Q is going to move in which direction? So positive charge carriers will always move along the direction of what? Along the direction of current. So it is moving in this direction, right? Okay. And B field here, B field is pointing in this direction. So we have considered this as X axis and Y axis and Z axis, right? So here B field is pointing in Z direction. Understood? So in this case, what we have observed here, the force experienced by the positive charge is equal to what? Q into velocity is in X direction and B field is in Z direction, Okay. So x cross z will be what? Minus y. Yes or no? So the magnetic force is going to experience in minus y direction. So that means all the positive charge carriers will come and accumulate at the bottom surface, and there will be a deficit of what? There will be a deficit of positive charge at the top. So the deficit of positive charge at the top, you can accommodate it as what here? You can accommodate it as negative charge. Okay. Okay. So so because of this magnetic force here, because of this magnetic force, what will happen? The charge separation has taken place. So because of this charge separation, what will happen? There develops an electric field. So here the electric field direction is in which direction here? The electric field is pointing from A to B. So this is the direction of electric field. Understood? Okay. So if this is the direction of electric field, what is the direction of electric force here? Here the charge carriers are nothing but what? Positive charge carriers. So always positive charge carriers are going to experience the electrical force along the direction of what? Along the direction of electric field. Yes or no? Okay. So we know that. So these positive charge carriers are going to experience the electrical force in upward direction. So from here, this is magnetic force, right? Okay. So the magnetic force is in y direction. The magnetic force is in y direction and electrical force is in upward direction. So both are opposite to one another. So after some time, what will happen here? At one stage, this electrical force will become equal to what? Will become equal to magnetic force. So that condition, we call it as what? We call it as equilibrium condition. So under equilibrium condition here, under equilibrium condition. So under equilibrium condition, so what happens here? This F electrical magnitude will become equal to what? F B. That is the magnetic force magnitude will become equal to what? Electrical force magnitude. Both are acting exactly opposite to one another. Right? Okay. So Rahul Thakur, good afternoon. Good afternoon, Thakur. Right? Okay. Okay, yeah. So this is what we have seen. This is what we have seen under equilibrium condition. So that means, see here, under equilibrium condition means the electrical force magnitude and magnetic force magnitude both are becoming equal and they are acting exactly opposite to one another. So that means now the net force acting on the charge will become equal to what? Under equilibrium condition, the net force acting on the charge will become equal to what here? The net force acting on plus Q will become equal to what? Tell me. If two forces acting opposite to one another and if their magnitudes will become equal. Okay, so then the net force acting on plus Q will becomes equal to what? Will becomes equal to, tell me here, will becomes equal to what? Tell me, Alok Kumar Thakur, tell me. Then what happens at one stage under equilibrium condition? The net force acting on the charge will become equal to what? Tell me. Will become equal to 0. Yes or no? Will become equal to 0. Right? Okay. So that means what is the net force here? The net force is nothing but what? Is nothing but, so write all the forces here. What are the forces? That is nothing but F electrical plus what? F magnetic. Understood? So this must be equal to what? This must be equal to 0. This must be equal to 0. Right? Okay. Okay, yeah. So from here, see here, what I am trying to do here is, see, already I have explained. 1 minute here. Okay. Okay, yeah. So see, already I have explained. Yes or no? Already I have explained in the previous class. Yes or no? Already I have explained all these things in the previous session itself, right? So F electrical plus F magnetic force will become equal to 0. So that means F electrical must be equal to what? Minus of F magnetic force. Understood? Okay. So keep all these points in mind here. right? Okay, so magnitudes will be equal, but if you consider the vector form, both forces must be exactly opposite to one another. And also in the similar way, we have analyzed for what here? We have analyzed by assuming it as what? By assuming it as n-type semiconductor. So whenever we assume it as an n-type semiconductor, the majority carriers will become what? Will become negative charge carriers, that is minus q. Okay, so minus q, the current is flowing in this direction, means the negative charge carriers are going to flow from right to left. Okay, so in this case we have observed that all the negative charge carriers will get accumulated at the bottom surface, and at the top surface there will be a deficit of negative charge carriers that can be accommodated as what? That can be accommodated as positive charge. Understood? Okay, so we have seen that if it is p-type, we have seen that VAB is what? VAB will be positive if it is p-type here, if it is p-type. Okay, so if it is n-type, then in this case VAB will become what? VAB will become negative. Understood? Okay, so all these things we have seen, right? Parasmoon, how electric force is upward? See, Parasmoon, I think you are not attending regularly, right? Okay, I have explained all these things here. Yes, I have explained all these things. See, whenever you are having F bar is equal to what? F bar is equal to E bar into Q. Yes or no? Okay, so if electric field is present in this direction, let us assume electric field is present in this direction. If you place a positive charge in this field, then it is going to experience a force in which direction? It is going to experience a force along the direction of what? Along the direction of field. Yes or no? Now here in this case, the direction of electric field and the direction of force, both are going to be in the same direction. Yes or no? Whenever you place a positive charge in the electric field, that positive charge will move along the direction of electric field. In this case, the direction of electric force and the direction of electric field, both are going to be what? Both are going to be same. Right. Now, if you place negative charge minus q, what will happen here? F electrical force in this case is equal to what? So minus q into what? Into E bar. So that means the force direction, the electrical force direction is exactly opposite to what? Is exactly opposite to electric field direction. That means a negative charge is going to experience a electrical force exactly opposite to what? Exactly opposite to the direction of electric field. So that means if you place a negative charge in the electric field, it is going to move against the field, because it is experiencing the electrical force in this direction, which is exactly opposite to electric field. Whereas if you place plus q, it is going to experience the electric force along the direction of field. Right? Okay, so I have explained all these things here, right? Okay. So Parasmoon, please go through the previous lectures also here, right? Okay. Okay, yeah, fine. So these things we have seen here in the previous session itself, right? Next. So next what we have done here is same principle here, or same concept. Based on the same concept, what I have done here is, so we have taken a conductor. Yes or no? We have taken a conductor, and we have this conductor, we have considered this conductor is moving with velocity v, so in magnetic field B. So we have considered a magnetic field, is pointing into the board. Okay, so every time I don't represent like this here, okay, so I don't represent sometimes this is circle, okay, but you have to understand, right? Okay, yeah. So this is the B field here, so B field is pointing into the board, right? Okay, so I have told you a procedure, how to determine the EMF or voltage induced at the ends of what? At the ends of this conducting material. So if you take a conducting material, or if you take a conducting bar, okay, of length, let us say its length is L here, L, right? Okay, so always we have considered the x-axis as in this direction, and this is y-axis, and this is z-axis. So that means here B field is in negative z direction, and here velocity is in x direction, right? Okay, so this we have considered. Let us consider this as y is equal to 0. So this point you can consider as B, and this is y is equal to L, and this point you can consider as A. Understood? So whenever you move a conducting bar in a magnetic field, we have seen that there induces an EMF across the conductor, or I can say there induces an voltage at the ends of what? At the ends of this conducting material. So we try to determine what? We try to determine VAB. Right? Okay. Okay, here. So I have told one method here. In order to determine this potential difference, or VAB, that is the potential at the ends of what? At the ends of conducting material. Understood? Okay. Okay, here. So why I have told that method means in that method we are going to follow each and every step here. That means we are doing the analysis. Understood? So what happens whenever the charge is whenever the conducting bar is moving in the magnetic field? What will happen? How the magnetic force direction will be? So because of this magnetic force, the charge separation will takes place. As the charge separation takes place, the electric field will get induced. So because of this electric field, there induces an electrical force. Yes or no? So this electrical force and this magnetic force will be exactly opposite to one another, and at one stage they will become equal. That is called as equilibrium condition. So under this equilibrium condition, there induces an voltage at the ends of what? At the ends of conducting bar. So all these things here, each and everything, in which direction the force will be induced. So all these things we can understand by following that procedure. So that's why I have told that lengthy procedure. Understood? Though it appears to be lengthy, there it is going to cover each and every point here. How you are determining the potential? So that is VAB is equal to what? Is equal to integral A to B E bar dot dl bar. So what you are going to get from here? Yes or no? How to write the electric field in terms of VAB? So all these things we have seen. Understood? So that's why I have explained that procedure here. So with that procedure, you can understand the concept clearly, because whenever you are doing that whatever the problems I have given as homework, okay, so if you would have done that homework, then you would analyze each and every step clearly. So then you will get familiar with that concept. Understood? Okay, so now I will tell you the simplest method here. Now I will tell you the simplest method to calculate the potential difference at the ends of what? At the ends of conducting bar. Understood? Okay. Okay. So why I have told that previous method is just make you to get familiar with the concept. Okay, so if I give you this simplest method, then you don't analyze each and everything here. So that's why I have not mentioned that simplest method yesterday. Okay. Okay, so now I will give you the simplest method to determine directly this potential across the conducting bar, right? Okay, so what is that method? See here. See okay, yeah. So see here. So here in this case what happens here? So whenever it is moving, so here we have considered, or okay. Okay, so here whenever it is moving, you are going to have what? Magnetic force, and after that what will happen? The electric force will also get developed. Understood? So that means here you are having both electrical force as well as what? Magnetic force, right? Okay, so now I am writing the Lorentz force equation here. Forget about all the other things here. Okay, just consider Lorentz force equation. So what is the Lorentz force equation? If both electric field as well as what? Magnetic field is present. Okay, so what is the Lorentz force equation? Tell me. So F bar is equal to what? That is F net is equal to what? Is equal to Q into what? Q into E bar plus what? Plus V bar cross V bar. So forget about all these things here. Forget about whatever I have told previously. Okay, now just consider what is the Lorentz force whenever you are having both electric field and magnetic field. So this is the Lorentz force here. Understood? Okay, so under equilibrium condition here, under equilibrium under equilibrium condition, we have seen that F electrical will be equal to what? Minus F magnetic force. F electrical is equal to minus F magnetic force, and here this net force will become equal to what here? Net force is nothing but what? Net force is nothing but F electrical plus what? F magnetic force. Yes or no? So under equilibrium condition, this F net force that is equal to F electrical plus what? F magnetic, this must go to what? This will become equal to 0. So from here we will get F electrical is equal to what? Minus F magnetic. Understood? Okay. Now here F electrical is nothing but I can write Q into what? Q into E bar. So this is equal to minus of what is the magnetic force here? Magnetic force is nothing but what? Q into V bar cross B bar. V bar cross B bar. Okay. So here I am telling you the second method here, simplest method. Okay. So what is that I am telling you here, right? Okay. So forget about all the other things, conducting bar, moving in the B field, everything you just forget. Okay, just listen to this one, right? Okay, so here what will happen here? Here Q will get cancelled. So therefore E bar is equal to what? E bar is equal to, I can write it as minus of what? Minus of V bar cross what? V bar cross B bar. V bar cross B bar, right? Okay. So this is important result here. This is important result. So E bar is equal to what? E bar we can write it as what here? Minus of V bar cross B bar. This is under what? You have to remember this. This is under equilibrium condition. This is under equilibrium condition. Only under this condition, these two forces, okay, the magnitude of these two forces will become equal and the directions will be opposite to one another. So only under this condition you can write the electric field as what? Electric field as minus of V bar cross B bar. Understood? Okay. Now if you want to determine the potential difference between any 2 points, okay, so in general I am saying, so let us consider VAB. So VAB is equal to, we know that it is integral A to B E bar dot what? E bar dot DL bar. E bar dot DL bar. Understood? Okay. So from here VAB is equal to integral A to B. Here electric field is nothing but what? Electric field we got it as what? Minus of V bar cross B bar. So I can write just substitute here. So what you are going to get? Minus of V bar cross B bar dot what? Dot DL bar. Okay. So if you want to determine the potential, if you want to determine the potential difference, okay, at the ends of the conducting bar, then you can directly use this formula. So VAB is equal to what? What we got here? So we have derived this formula here. Yes or no? Okay. So VAB, how you can write? Integral A to B minus of what? V bar cross B bar dot DL bar. Understood? Okay. So you can directly use this formula. Okay. So now if you want this one here, you can write as what? Or you can write it as minus of V bar cross B bar. You can write it as what? You can write it as B bar cross V bar. B bar cross V bar. Understood? In this manner also you can write. By removing minus, you can write it as B bar cross V bar. Understood? Okay. So that's your wish here. But just to follow this one here. Okay. Okay. So this is the formula we got. Right? Okay. So now so we are going to use this formula directly to determine what? To determine the potential that is developed at the ends of what? At the ends of the conducting bar. The potential difference at the ends of what? At the ends of conducting bar. Understood? So we are going to use directly this formula. Right? Okay. Okay. So what is that one here? See here. So VAB. Okay. So what we can use directly? VAB is equal to what? Integral A to B minus of what? V bar cross B bar dot DL bar. So just apply to this one here. Just apply to this one. So what you are going to get? Within one step you are going to get the answer. right? Okay, so the velocity is in which direction here? X direction. And the magnetic field is in which direction? Negative Z direction, right? Okay, and this differential length dl bar, that means along the length of what? Along the length of the conducting bar. So along the length of the conducting bar, what is the variable? Is nothing but y. So you can replace dl bar with what? Dl bar with dy ay cap, dy ay cap. Understood? So here what you are going to get? Integral a to b minus of what? Minus of v into b into what? So x cross z here, x cross z is minus y. So minus of minus will become plus. Minus of minus will become plus. So here you can write vb ay cap dot what? Dot dy ay cap, dy ay cap. Understood? Okay? Okay. So now see here, so this is equivalent to, so minus Vb, V is velocity which is constant, B field is also constant or uniform, so you can take it out of the integration. So what you are going to get? Minus Vb integral what? Integral dy a to b, so that is equal to minus Vb, so this is velocity here, this is velocity. So I am representing this velocity with this letter. Okay, so Vb integral dy is y. So if you substitute the range, you are going to get b minus a. So that is minus Vb into b minus a. B is equal to what? At point B, y value is equal to 0, and at point A, y is equal to what? L. Okay, so b is equal to 0 and a is nothing but what? L. So what you are going to get? VAB is equal to what? Is equal to minus into minus will become plus. You are going to get simply BLV. Okay, so VAB is nothing but what? Positive. So since VAB is positive, that means A must be what? A must be at point A must be at higher potential, and B must be at what? B must be at lower potential. That means at A here, that means at this end, what must be accumulated here? What must be accumulated? Positive charge must be accumulated. Yes or no? Positive charge must get accumulated, and at the bottom, negative charge must be accumulated. Understood? Okay. Okay. So previously, what we have done? We have analyzed each and everything. So that finally we try to get the potential difference between A and B. So now what I have told here, so now you have understood the concepts each and everything clearly. So now there is no need to follow that bigger procedure here, lengthy procedure. Understood? So you can directly use this formula. You can directly use this formula to get VAB. So now here VAB we are getting positive. That means now without any analysis you can say top is what? Positive, and bottom is what? Negative. Okay, top is at positive potential and bottom is at a lower potential. Understood? So in this manner you can directly tell by using through this formula also. Understood? Okay, but we have to understand here, the main thing is with the help of this formula I would have explained this within 10 minutes. Understood? But it is not going to be that much helpful here. Okay, you have to understand, just blindly following the formula doesn't give you the feel of the subject. Understood? So first you have to understand and analyze the concept, right? Okay, so once you have understood each and everything clearly, then we have to search for shortcuts, right? Okay, right. Anil, good evening. Parasmun, how to take the direction of DL? Parasmun, you are asking again and again the same things here. What I have to do? DL bar here, the differential length, it is along which direction? This length is along which direction? Y direction or not? Yes or no? So I am considering DL bar as what? Dy ay cap. So what I have told here, whenever you are doing the line integration, always consider this as what? Positive. Because the limits are going to take care of what? Take care of the direction. That's what I have told many times whenever you are doing the line integration, right? Okay, so here DL, the differential length is this length is varying along which direction? This length is varying along y direction. So DL you have to replace with what? Dy, right? Yes or no here? Okay, so is this clear here? VAB is equal to BLV. Is this clear? Is this clear? Tell me. Rahul Thakur, Alok Kumar, tell me here, is this clear? Parasmoon, is it clear? Tell me. Parasmoon, please go through the previous lectures also, right? Okay. See, that's the problem. If you are not having continuity now, so then again it will be like first class, right? So if you miss 1 or 2 lectures or 3 lectures continuously, then again it would be like new things. Everything will looks like new, right? Okay. So that's why you have to be in touch with the subject. You have to be in touch with the subject. So that's why I am saying keep revising at regular intervals of time, right? Okay. Then you won't get any doubts, right? Okay. Okay. So now I will give you one problem. You have to tell me the answer here. You have to tell me the answer. Okay. So here I have considered a conducting bar, right? Okay. Now let us say the magnetic field is pointing out of the board. The magnetic field here I am considering it is pointing out of the board, right? See, if it is not possible for you to attend the live session, okay, so it is available now. Once the class is completed, that video lecture is available in YouTube itself. Yes or no? Okay, so you can just go through that, right? Okay. So this is B field here. This is B field. Okay. So now this conducting bar is moving with velocity. Okay, I will take conducting bar in this manner here, not in this manner. Okay. So this is B field, right? Okay. Now I will take the conducting bar like this. This is the conducting bar here. This is the conducting bar. This is the conducting bar and this is the B field. Now let us consider this conducting bar is moving with velocity v in downward direction. Now tell me, let us consider this point is A and this point is B. Right? Okay. Okay. So now here consider this as what? This as x-axis and this as what? This as y-axis and this as what? This as z-axis. Okay. Now tell me here. Now tell me VAB. Now tell me VAB. So VAB is positive or negative? What you are going to get? Tell me. What is VAB? Tell me. What is VAB? Tell me. Tell me here. Just now I have told you what you have to use. Now you are very much clear with the concept, so you can directly use this formula, that is VAB is equal to what? Minus of integral E bar dot DL bar, that is minus of V, you can write. Okay, VAB is equal to integral A to B minus of V bar cross B bar dot what? Dot DL bar. You can use this formula directly and tell me the answer here. Tell me the answer. Tell me the answer, what you are going to get. Alok Kumar, Rahul Thakur, tell me. So always write this as VR. Write velocity like this here, okay, so that we can differentiate between velocity and potential. Tell me what you are going to get VAB. BLV. So you are getting plus BLV. Rahul Thakur, you are getting plus BLV. So that means you are saying VAB is positive. You are saying VAB is positive. Okay. So I got one answer here. So that is BLV. That is BLV, right? Okay. So that means it is plus BLV. So one answer I got it as positive value. That is plus VAB. Next, Alok Kumar, negative x direction. What is negative x direction here? What I am asking? I am asking this potential difference VAB. VAB is positive or negative? That's what I am asking. So Rahul Thakur told BLV, so it is positive, he is saying. That means the potential at A is greater than the potential at B. So that's what he is saying, right? So that's what I am asking here. What you are getting? Whether you are getting, we know that final expression is going to be BLV, right? Okay. So now what I am asking is, it is plus BLV or minus BLV? That means at which end the potential will be more? That's what I am asking. Right? Tell me here. Alok Kumar. So I will give 20 more seconds here. Okay. 20 more seconds I am giving. So you also got plus BLV. Okay, right. So let's check here. Let's check whether you are getting the same thing or not. Okay. Now here the velocity is in which direction? Downward direction. So downward direction means it is in negative y direction. So here the velocity is in negative y direction. And B field is pointing out of the board. B field is pointing out of the board means B field is in positive z direction. Understood? And here dl bar is nothing but what? This is along the length of the rod. So that is nothing but dx ax cap. Dx ax cap. Right? Okay. So what you are going to get? Integral a to b minus of what? Minus of v into b. So here y cross z here, if you do ay cap cross az cap, it is going to result in what? Ax cap. Here already minus is present. Yes or no? Here already minus is present. So you are going to get minus ax cap dot what? Dot dx ax cap. Right? Okay. Now here minus and here minus. Now here minus will get cancelled. You are going to get what? You are going to get integral a to b vb. This is velocity here. This is velocity vb into what? Into dx. Right? Okay. So this is equal to v into b. Integral dx is nothing but x from a to b. So that is equal to what? V into b into what? B minus a. B minus a. So at point b here. At point b. So at point B, see A is at this location, yes or no? Okay, and B is at this location. So as you move along this direction, the length is going to what? The length is going to increase. So let us consider here let us consider this is x is equal to 0. Let us consider, and let us consider this point as x is equal to L. Understood? So B value is L and A value is what? A value is 0. So B value is L and A value is what? A value is 0. So you are going to get what? You are going to get BVL. So you are getting positive. You are getting positive. So that means VAB you are getting what here? VAB you are getting positive. So that means at A end here, at this end, what is the charge that will get accumulated here? What is the charge that is accumulated? So here you are going to have positive charge, yes or no? And here negative charge will get accumulated. Negative charge will get accumulated. Understood? Okay. But if you want to, now here the electric field here, the electric field is going to point in which direction? Electric field is going to point in this direction. Electric field is going to point in this direction. Okay. Now if you want to analyze what is the direction of magnetic force, what is the direction of electric force, okay, that we can analyze here. So already I have told how to analyze all these things, right? Yes or no? Okay. Okay. Yeah. So you can directly tell whether it is positive or negative just by using what? Just by using this formula, right? Okay. Okay. Yeah. So next here, next. Okay. Okay, yeah. So next, in case of semiconductors also, yeah, in case of semiconductors also, okay, in case of semiconductors also, you can apply the same thing here. You can apply the same thing. See here, how easily we can get the answer. See here. In case of semiconductors also, okay, so instead of that lengthy procedure, you can directly follow this procedure here. So what I have told, if suppose let us assume this is p type, then the charges will be plus q. So here the current is flowing in this direction. So here the velocity is in which direction? X direction. Understood? Okay, now here VAB, let us say this is A and this end is what? B. Understood? Okay, so let us consider this is y is equal to 0, and let us consider this end is y is equal to h or something, h or l, whatever you want you can put, right? Okay, okay, so now in this case VAB is equal to what? Integral a to b, integral a to b, e bar dot dl bar, e bar I can write it as minus of what? V bar cross what? V bar cross b bar dot what? Dot dl bar. Now here integral a to b minus of what? Velocity is in which direction here? Velocity is in x direction, velocity is in x direction, and b field we have considered in z direction. Yes or no? This is x and this is y and this is z, right? Okay, so b field is in z direction. So what you are going to get? X cross z minus y, so you will get vb minus ay cap. Okay, so dot here, this is along this direction here, along this one. Okay, so along this direction the variable is nothing but what? Y. So dl bar I can write it as what? Dy ay cap, right? Okay, so from here also what you are going to get? Integral a to b, v into b into, okay, b into dy, right? So here minus into minus will become plus. So this is equal to what? This is equal to v into b into okay, integral dy is y. If you substitute the range, that is b minus l, b minus a. Okay, so at b what is the value here? At b the value is h. Okay, the value is h. At a it is 0. Okay, so what you are getting? B into v into h, b into v into h. So this is nothing but what? This is nothing but VAB. So that means we are getting VAB as what? Positive. So that means here it must be what? Plus, and here it must be what? It must be negative. This is for p type. So in this manner we can easily analyze here, right? Okay, so first you have to understand the concepts and that analysis clearly, then we can apply this shortcut methods for problems here. For problem solving you can use this shortcut methods. Understood? But in order to analyze each and everything, you have to follow the previous procedure. Whatever we have done, each and every step will be clear, right? Okay, so I hope all these things are crystal clear here. I hope all these things are crystal clear. Yes or no here? Is it clear? Alok Kumar, Rahul Thakur, Paras Moon, right? Okay, so I hope each and everything is crystal clear here. Okay. Okay, so now I will give you one more problem here. I will give you one more problem. You have to tell me the answer. See, up till now what I have done here is we have taken a conducting bar and we have moved with velocity v in some b field, So in this manner we have done the problem. Now what I am going to do here is, so just I am going to slightly change this problem here. So what I am going to do here, see here. So now here I am considering the B field here. I am considering the B field is pointing into the board. I am considering the B field is pointing into the board, right? Okay, okay. So now see here. So let us consider from this point. Okay, okay. Now let us consider this as conducting bar. Okay, so this is we can call it as pivot point here. Okay, so it is hanging at this point, right? Okay, so now let us say this is conducting bar. This is conducting bar. Okay, now let us assume this is B field. So this B field is pointing in negative Z direction. So let us consider this is X axis and Y axis, and this is Z axis, right? Okay, so B field is pointing into the board, right? Okay. Now let us consider this is A, this point I am considering as A, this point I am considering as B, right? Okay, so now here let us consider this conducting bar. This conducting bar is revolving here, is revolving in this B field. Okay, so it is revolving with an angular velocity, omega. Okay, now here this is the B field. Here you are having the conducting bar. Previously we have taken the conducting bar and it is moving like this. Yes or no? Now we have taken the conducting bar here, and now it is revolving about this point here, about this point. So this is called as pivot point. It is hanging here. Okay, so it is fixed at this location. Now what is happening? So this conducting bar is revolving in this B field, with an angular velocity omega, Then you have to determine VAB. Understood? The concept is same here. Previously it is moving like this, now it is moving in this plane. Yes or no? It is revolving in this plane. Understood? Okay, okay. So now how to determine VAB in this case? Now let us consider I hope you have seen that cylindrical coordinate systems. Yes or no? I hope you are familiar with cylindrical coordinate systems that I have explained already, right? Okay, so now here what I am considering here is along this length here, I am considering the variable as what? The variable as rho. Along this length I am considering the variable as what? Variable as rho. So at this point I am considering rho equal to 0, and at point B I am considering rho is equal to what? Rho is equal to L. Understood? So the variable along this length I am considering as what? Rho, and at this end rho is equal to what? 0, and at this end rho is equal to what? Rho is equal to L. Understood? See, whenever this conducting bar is revolving, it is going to trace what? It is going to trace a circular path. Yes or no? It is moving in a circular path. Understood? Okay, so the radius, the length of this conducting bar is nothing but what? It will become the radius. Understood? Okay, now here I am considering at this end rho is equal to what? Rho is equal to 0, and at this end rho is equal to L. So that means the length of this conducting bar is nothing but L. But here the variable I am considering as what? Considering as rho. Okay, now if suppose anything that is circulating, if it is circulating in which direction here? In anti-clockwise direction. Understood? Okay, so this direction here, I am considering it as what here? A phi cap. See, I hope you have studied this cylindrical coordinate system here. X axis here, Y axis here, Z axis here, right? Okay, so so if I consider a cylindrical coordinate system, okay, so the movement along this circular path here, is given by what? Is given by phi. Understood? And what is the unit vector along phi here? Is nothing but A phi cap. Understood? So here this is revolving along a circular path in anti-clockwise direction. That means the direction the direction in which it is revolving, I can consider it as what? I can consider it as a phi cap. Understood? Okay. So if you go through this cylindrical coordinate system, whatever I have explained, then it is going to be very much clear here. Okay. 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 So if it is circulating like this, okay, in anti-clockwise direction. So this direction we can call it as what? We can call it as a phi cap direction. Understood? Okay. So this direction, this is circulating direction, I am calling it as a phi cap direction. Right? Okay. Yeah. Okay. So in cylindrical coordinate system, what are the variables? Variables are nothing but what? Rho, phi and z. Unit vectors are nothing but what? A rho cap, a phi cap, a z cap. This is radial direction. This is what? This is along the circumference of what? Along the circumference of circle. Yes or no? So this is the tangent. A phi cap will give you the tangential direction at any point on the circumference of what? At any point on the circumference of the circle. A z cap is nothing but it is the unit vector along z direction. Okay. So you have to go through this cylindrical coordinate system here once. Right? Okay. Yeah. Fine. Fine. So now tell me what is VAB here? What is VAB in this case? So VAB is equal to what? VAB is equal to, just apply the formula here, that is equal to integral A to B. Integral A to B minus of what? Minus of V bar cross what? Minus of V bar cross B bar dot what? Dot DL bar. Minus V bar cross B bar dot what? Dot DL bar. Okay. Now here this DL bar will be along the what? Along the length of the conductor. So along the length of the conductor, what is the variable here? Variable we have considered as rho. So that means you can replace this DL bar with what here? This DL bar you have to replace with what? You have to replace with D rho A rho cap. And here this velocity, the velocity is in which direction? It is revolving. It is revolving in anti-clockwise direction. Yes or no? It is making a circle. It is making a circle in anti-clockwise direction. Understood? So that means the velocity is in a phi cap direction. So the velocity I am considering is in which direction here? A phi cap direction. And B field is pointing in which direction? Into the board. Into the board is nothing but what here? Z direction. Sorry, negative Z. So B field is pointing in negative Z direction. Is this points clear here? Tell me. So once you are clear with in which direction the velocity, in which direction the B field, and what is this DL bar, if you understand these things, then it is completed. Yes or no? Okay. Is it clear here up till now? Tell me. Paras Moon, Alok Kumar, Rahul Thakur, tell me here. Is it clear up till now? Tell me. Tell me here. See, radial direction we consider as rho, right? And along the circumference of the circle we consider the direction as what? A phi cap if it is in anti-clockwise direction. Understood? Okay. And AZ cap will be perpendicular to the plane. AZ cap is perpendicular to the plane. See here, this is cylinder here, right? Okay. So this is radial direction, aero cap, right? And if you draw the tangent on the circumference of the circle, it is going to point in what? In anti-clockwise direction. It is going to point in A phi cap direction, and AZ cap is will be in this direction. That is, in this direction will be AZ cap, right? Tell me here, is this clear? Rahul Thakur, Paras Moon, Alok Kumar, tell me here. No, I am not asking the answer. Are you have you understood these directions? That's what I am asking. Right? Okay. See here. Right, see here. VAB is equal to integral A to B minus of what? Minus of here you are having A phi cap cross minus AZ cap. So what is A phi cap cross AZ cap here? A phi cap cross AZ cap is nothing but aero cap, but here you are having minus. That means the resultant direction here is nothing but minus aero cap. Okay, so here minus of, you are going to get V into B into what? Into minus aero cap, minus aero cap. Right? Yes or no here? A phi cap cross AZ cap will be aero cap. Here minus is present, so minus aero cap. Already here minus is present. So dot d rho aero cap, d rho aero cap. Right? Okay. Now see here. So integral A to B. Here integral A to B. So here minus into minus will become plus. So V into B into D rho. V into B into D rho. So this is what we got here. This is what we got. Now here they have given what here? They have not mentioned anything about V. Yes or no? So what they have given? They have given omega. Omega is nothing but what? Angular velocity. Yes or no? So they have not given here. You should not consider the linear velocity. You should not consider the linear velocity. You have to consider what? You have to consider the angular velocity. Right? Okay. Because here it is rotating, here it is revolving. Yes or no? So whenever it is revolving, you have to consider what? You have to consider the angular velocity. Right? Okay. So now what is the relation? We have written the expression. We have written the expression in terms of linear velocity. Now tell me, what is the relation between linear velocity and angular velocity? Do you know the relation between linear velocity and angular velocity here? Tell me. Do you know the relation between linear velocity and angular velocity? Tell me. Tell me here. What is the relation between linear velocity and angular velocity? What is the relation between linear velocity and angular velocity? Yes? You know the relation between linear velocity and angular velocity? You know or you don't know? Tell me here. Rahul Thakur, Alok Kumar, Paras Moon. Tell me. V is equal to what? V is equal to R omega. Very good here. V is equal to R omega. See here, if I consider, this angle as d phi here, this angle as d phi. Okay. So here this arc length is nothing but what? Is nothing but dl. This arc length is nothing but dl. So dl is equal to what? dl is equal to rho into what? Rho into d phi. Rho into d phi. Understood? Okay. So now what is the linear velocity here? So dl by dt will give you the linear velocity. So that is equal to what? Rho into what? Rho into d phi by what? D phi by dt. So dl by dt is nothing but linear velocity v, which is equal to what? Rho into d phi by dt is nothing but angular velocity, that is omega. That is omega. So linear velocity v is equal to what? Is equal to radius of the circle multiplied by what? Multiplied by angular velocity omega. V is equal to rho omega. V is equal to rho omega. Okay. Okay. So I will tell its a physical significance later here. So whenever there comes a situation, okay, so at that moment I will tell you why, what is the physical interpretation of this relation. Okay. So I will take any one problem here, there I will explain the physical interpretation of that relation also. But as of now let's just take that expression here, that is V is equal to what? V is equal to rho into omega. So if you do this, what you are going to get? Integral a to b, V is equal to what? V is equal to rho into omega into what? B into d rho. into d rho. Now if you observe here, what are the constants here? What are the integration constants? Tell me. So you can take all the constants outside the integration. Now here what are the constants? Omega is constant, and B field is also constant. Yes or no? Now you can take omega and B are integration, what I am saying here, omega and B are independent of what? Are independent of this integration variable. Omega and B are independent of this integration variable. So you can take it out of the integration. So omega into B, integral A to B, rho into d rho. So that is equal to what? That is equal to omega into B. What is integration of rho here? Integration of rho is nothing but what? Rho square by 2. Rho square by 2. So integral A to B. Integral A to B. Right. Okay. So what you are going to get here? Omega into B divided by 2. Here substitute, you are going to get B square minus what? B square minus A square. So now here at point B, okay, so at point B here rho value is what? L, and at point A rho value is equal to what? 0. Yes or no? Okay. So here at point B, here rho value is L, that is L square you are going to get, A value is 0, that is 0 square. Yes or no here? You are substituting the values of rho or not? Okay, so B square means at B rho value is L, that is L square, minus what? At point A rho value is 0, so that is 0 square. So what you are going to get? You are going to get B omega into L square divided by what? Divided by 2. So this is the potential difference between A and B. See how the expression has changed, see here, right? Okay, so this is the potential difference. This is the potential difference that you are going to get at the ends of what? At the ends of conducting bar. Okay, so if you take a conducting bar, okay, so if you rotate this conducting bar here, if you rotate this conducting bar in the magnetic field, see if you observe here the velocity, or you can consider velocity. Okay, so the velocity is in which plane here? The velocity is in this plane. Yes or no? And B field is pointing into the board. Yes or no? So that means the direction of B field, right? And the velocity, that means the plane in which we are considering the velocity, both are what? Both are perpendicular to one another. Yes or no? Okay, so this is the plane or not? This is the plane we are considering. So the velocity is in A phi cap direction, that is in this plane, and B field is pointing into the board. That means the direction of B field and the direction of velocity, both are what? Both are perpendicular to one another. Yes or no? Velocity is in A phi cap direction, right? Okay, and B field is in which direction? B field is into the board, that is in negative Z direction. Understood? Okay, so that means B field and velocity both are perpendicular to one another. So previously also whenever you have considered a conducting bar, so in this case also, okay, so whenever it is moving like this, with velocity V, here also what? The velocity and B field both are what? Both are perpendicular to one another. Okay, so remember these things here, Have you understood this expression here? Tell me, is it clear? Is this point clear? Tell me. So that's why just don't remember anything as formulas, right? Okay, so just apply the concept and follow the basic procedure. Okay, whatever I have told, just follow that. So finally you are going to end up with the correct result, right? Okay, is this clear here? Tell me. Yes, Rahul Thakur, clear. Okay, right. Alok Kumar, are you there? Okay. Alok Kumar, is it clear? See, if you are having any doubts, please ask me here. Please ask me. If you are having any doubts up till now, please ask me here. I will clarify those doubts. Tell me. Okay. So I hope this is crystal clear. Right? Okay. Okay. So now you are ready to solve one gate problem. See here, I am going to give you one gate problem. You have to tell me the answer. See, don't just apply the formulas. Understood? Okay. Don't take for all the whatever, if the conducting bar is rotating in B field, then don't always take VAB is equal to B omega L square by 2. Okay. So this is for this case. Okay. It is very simple expression or not? Okay. Just you have to follow this one. Just you have to follow this one. So if you follow this one, then you are end up with the correct result. Understood? So don't remember anything blindly here. Right? Okay. Okay. Here. So now I will give you one problem. I am expecting the answer from each and every one here, from each and every one. Okay. You have to tell me the answer here. If you want, you can take 1 minute or 2 minutes time also, but I want answer. Right? Okay. Okay. Okay, so you have to tell me the answer for this question. See, what is the question they have asked? See here, this question is given in gate 16 for electrical students. See here, a rotating conductor of 1 meter length, is placed in a radially outward about z-axis, magnetic flux density, that is about z-axis here. Okay, so this is z-axis here, and the magnetic field intensity, the magnetic flux density B bar is pointing in which direction? It is radially outward. So this is z-axis. So the B field they have given as it is pointing radially outward. Understood? Okay. Okay, that's what they have given. A rotating conductor of 1 meter length is placed in a radially outward magnetic flux density B of 1 Tesla, as shown in figure below. So conductor is parallel to and at 1 meter distance from the z-axis. So this is the conducting bar here. So it is placed along what? Along z-axis. Understood? Okay. And it is at a normal distance, radial distance or normal distance at rho equal to what? Rho equal to 1 meter. Understood? Okay, that's what they have given here. This conductor is parallel to and at 1 meter distance from the z-axis. So this conductor is parallel to z-axis and is at a distance of 1 meter from the z-axis. Understood? Okay. So the speed of the conductor in RPM required to induce a voltage of 1 volt across it should be. So the distance from the z-axis is parallel to and at 1 meter distance from the z-axis. The speed of the conductor in RPM required to induce a voltage of 1 volt across it should be. So that means here this is the z-axis here. Okay, so the B field is radially outward. So that means B field is in which direction? Rho direction. It is in rho direction. Understood? Okay. Now here parallel to this z-axis, they have placed a conducting bar here. And the normal distance from the z-axis to this conducting bar is nothing but what? Is nothing but 1 meter. Understood? Okay. So here you are having a conducting bar and the B field is pointing radially outward. Right? Okay. So now what they are doing here is now this conducting bar is revolving around this what? Around this z-axis. Now this conducting bar is revolving in this z-axis. Now just now we have seen that whenever a conducting bar moves in a magnetic field, whenever a conducting bar moves in a magnetic field. So here the magnetic field and the velocity, that means the velocity with which it is moving, okay, both must be what? Both must be perpendicular to one another. Understood? Now here the velocity of the conducting bar is in which direction here? Is in which direction? It is in a phi cap direction. Understood? And B field is pointing in which direction? Arrow cap direction. Understood? So we know that whenever a conducting bar moves in a magnetic field, then there induces a voltage or potential difference across it. Understood? Okay. So now now what they are asking is, what must be the speed? What must be the speed of this conducting bar in RPM, that is revolutions per minute, required to induce a voltage of what? 1 volt. Okay. We know that whenever it is revolving in a B field, there induces a potential, there induces a potential difference at the ends of what? At the ends of the conducting bar. They have given that for the potential difference to be 1 volt, for the voltage to be 1 volt, then what must be the speed? What must be the speed in RPM? What must be the speed of this conducting bar in RPM? Okay, with how much speed you have to rotate this conducting bar such that the potential difference across at the ends of the conducting bar must be equal to what? Will become equal to 1 volt. Okay, so that's what they are asking here. That's what they are asking. Okay, so tell me the answer here. Tell me the answer for this one. Just to follow the procedure here. Just to follow the procedure. Right. Just to follow the procedure. So let us consider here the variable is z, right? Okay. So here the variable here is z, right? So here let us consider this is z is equal to 0, and let us say this is consider this end is z is equal to L. Now consider this as point A and this as what? Point B. This end as point B. Understood? Now just try to determine VAB. First tell me what is the expression you got for VAB. So first tell me this expression here. First tell me this expression. So B field is radially outward. So in this B field, a conducting bar is revolving about this z-axis. So with what speed? With what speed in RPM you have to rotate this conducting bar such that the potential or the voltage across the conducting bar has to become what? Has to become equal to 1 volt. Okay, so that's what they are asking. Tell me here, tell me. B field is radially outward, that means it is in arrow cap direction, and this conducting bar is revolving. This conducting bar is revolving. Understood? Okay, so that means the velocity will be in which direction? A phi cap direction. Now whenever it is revolving, you have to consider what? You have to consider the angular velocity, right? Okay. So first represent in terms of V, okay, then replace V with what? With omega into rho, where rho is the radius of the circle, radius. Okay. How much you are getting? 1 RPM. Rahul Thakur is getting 1 RPM. RPM means what here, Rahul Thakur? Revolutions per minute, right? Check your answer. RPM means revolutions per minute. See, frequency, what do you mean by frequency? The number of revolutions per second, right? Frequency F means what? F means the number of revolutions per second. So that means if you determine F here, that is number of revolutions per second, then you can determine the number of revolutions per minute. Yes or no? So once check your answer, Rahul Thakur. I think you have done correctly, but you have done some mistake. Please check that. First tell me what is the expression you got, VAB. What is the expression you will get, VAB? Tell me. Just tell me this expression here. So 1 minute time here. So within 1 minute, let us see how many of you will get answer. So just tell me VAB. That's fine. Just to tell me VAB. I mean, what I am asking is, I am asking the expression for VAB. See, the conducting bar is revolving now. Yes or no? It is revolving. Right. So whenever it is revolving, you have to consider what? You have to consider angular velocity. So that's what I have said. Right. We have to represent in terms of what? In terms of angular velocity. First we are having the formula in terms of linear velocity, right? Okay, so first write the expression in terms of linear velocity, then in place of linear velocity, just replace with what? Replace with angular velocity. And we know the relation between linear velocity and angular velocity. So with the help of that relation, just replace linear velocity with angular velocity. That's it. Okay. Tell me here. B field is in arrow cap direction. The velocity is in a phi cap direction. Yes or no? It is revolving in anti-clockwise direction. So that is in a phi cap direction. Understood? Okay. So I am giving each and everything here. Just apply the formula here. That's it now. VAB is equal to what? Tell me. VAB is equal to what? Integral A to B V bar cross what? V bar cross B bar. Velocity is in a phi cap direction. B field is in arrow cap direction. Dot what? Dot DL bar. Dot DL bar. So this is along the length of the conducting bar. So that is nothing but DZ AZ cap. DZ AZ cap. So I have given everything here. So before I complete, at least tell me the expression here for VAB. Tell me. So integral A to B. Here A phi cap cross arrow cap. A phi cap cross arrow cap is nothing but what? So arrow cap, A phi cap, AZ cap. These are the unit vectors, right? So A phi cap cross arrow cap is nothing but what? Minus AZ cap. Minus AZ cap. So I am writing here V into B into minus AZ cap. Minus AZ cap. Right? Dot DZ AZ cap. Okay. So what you are going to get? This is equal to integral A to B. So what you are going to get here? So here, wait. VAB is equal to minus of, now I forgot, see here. You have to put minus of V bar cross B bar dot DL, right? Okay, so here you are going to have minus, right? Okay, so minus into minus will become plus. So you are going to get V, B, D, Z. Now here you have to replace V with what? V with what? What is the relation between velocity and angular velocity? V with, you have to replace with rho into omega, where rho is nothing but what? Where rho is nothing but the radius. This radius here, this radius is nothing but rho. Okay, so V you can replace with rho into omega. So this is equal to what? Integral A to B rho into omega into dz. Rho into omega, here you are having B. Okay, so this is equal to what? So B is constant, rho is also constant with respect to this integration variable, omega is also constant with respect to integration variable. Integral dz is nothing but z, its range is from A to B. So that is equal to what? B rho omega into B minus A. So at A, z value is what? At A, z value is equal to 0. At B, z value is equal to what? L. So you are going to get L minus 0, that is L. Okay, so this is the expression you are going to get. B rho into omega into L. So this is the expression for what? This is the expression for VAB. Anybody got this expression here? Tell me. Anybody got this expression? Tell me here. Anybody got the same expression? Rahul Thakur, Alok Kumar, Paras Moon. Anybody got this same expression? Tell me. So we got VAB is equal to what? Is equal to rho into omega. So B into rho into L into omega, right? Okay. So this is equal to what? This is equal to, now they have given they have given the potential as what here? The potential they have given as what? They have given as 1 volt. It induces a voltage of 1 volt, right? Okay. So consider VAB is equal to what? 1 volt, and B field they have given as 1 Tesla, right? 1 Tesla, and rho, that is the radius here, that is the radius. So this radius also they have given as what? Rho as 1 meter. So rho is also equal to 1 meter. Okay. So rho is equal to 1 meter. The length of the conductor, the length of the conducting bar is also, I think it is also 1 meter, right? So a rotating conductor of 1 meter length, that means the length of the conducting bar is also 1 meter. So the length of the conducting bar is also 1 meter. So multiplied by what? Multiplied by omega. So 1 into 1 into 1 will be 1. So therefore we are getting omega is equal to what? Omega is equal to 1. Omega is equal to 1. Right? Okay. So omega is equal to 1 radian per second. 1 radian per second. So from here I am going to determine f here. So omega I can replace with what? 2 pi f. 2 pi f is equal to what? Is equal to 1. Therefore f is equal to what? F is equal to 1 by 2 pi. So the frequency will represent what here? Frequency represent the number of revolutions per second. The number of revolutions per second. Okay. So f is equal to 1 by 2 pi is nothing but the number of revolutions per second. But they are asking the number of revolutions per minute. So what you have to do here? Tell me here. Tell me here at least. Tell me. Rahul Thakur, if you want to determine the number of revolutions per minute, what you have to do? What you have to do here? This is number of revolutions per second. If you want to convert it into number of revolutions per minute, then what you have to do? Tell me here. So therefore, number of revolutions per minute is equal to what? Is equal to, I can write it as 1 by 2 pi revolutions by, I have to convert these seconds into minutes. Yes or no? Okay. So 60 seconds is equal to what? 1 minute. So 1 second you can write it as what? 1 by 60 minutes. Right. So 1 second here, in place of second you can write what? You can write 1 by 60 minutes. Okay. So therefore this is equal to what here? This is equal to, here 2 ones and here 2 30s. So you are going to get 30 by pi revolutions per minute. Okay. So this is the number of revolutions per minute here, 30 by pi. But here I am not getting any response from chat box. Is this clear? Tell me. Rahul Thakur, Alok Kumar, Paras Moon, tell me here. Is it clear? Okay. So now I am getting 1 by 60. Now I am getting the response as 1 by 60 now. Okay. So I think it is a very much delay. Okay, there may be a very much delay between you and me here. I think so. Right. Okay. So this is the number of revolutions per minute. So what is 30 by pi here? What is 30 by pi? You just calculate this one. 30 divided by pi. 9.549. Okay, so you will get 9.549 revolutions per minute. Okay, so this is the answer here. This is the answer, right? Okay. Okay. So I hope this problem is also crystal clear here, right? Okay. See, just you have to apply the concept and follow the procedure. That's it, right? Okay. Okay then. So with this here, I am going to wind up the session for today, right? Okay. So if you are having any doubts, you can ask me here. If you are having any doubts, you can ask me. So otherwise, I will wind up the session for today. Is there any doubts here? Is there any doubts? Tell me here. Rahul Thakur, Alok Kumar, Paras Moon. Tell me. Tell me here. If you are having any doubts, please tell me. Is each and everything clear? Is everything crystal clear? Or if you are having any doubts, please ask me. Alok Kumar, repeat this one more time. Okay. See, Alok Kumar, they have given here z-axis, right? So this is z-axis, and here the B field is radially outward. B field is radially outward. So this is B field, right? Okay. So that means the B field is in radial direction, that is in rho direction here, rho direction. Understood? Okay. So it is just like this. So just I am drawing a rough diagram here. That's it. Okay. Now here, what they have done here is diagram is not looking good. Okay. Okay. So here this is z-axis here. So B field is radially outward. B field is everywhere radially outward. That means they have given B field is in aero cap direction. B field they have given in aero cap direction. Understood? Okay. So now here the B field is like this. Now here they have placed a conductor. They have placed a conductor. Okay. I will take. Okay. So let us consider this as what? This as a conductor. This as conductor. So this is z-axis. So this is conductor. So here the B field is pointing like this here. So B field is radially outward. Radially outward. Understood? So they have placed a conducting bar here. Understood? So the distance from the z-axis to this conducting bar is 1 meter, and the length of this conducting bar is also 1 meter. So B field is in aero cap direction, radially outward direction. Now what they are doing here is they are rotating this conducting bar. They are rotating this conducting bar about this z-axis. This conducting bar is rotating about this z-axis. Understood? Like this. Okay. So if the conducting bar is rotating in this direction, it is rotating in anti-clockwise direction. That means the direction of velocity, you can consider in which direction? A phi cap direction. Yes or no? The velocity of this conductor you can consider in A phi cap direction, and B field is in aero cap direction. Now what they are asking is how many revolutions per minute it has to complete such that that means they are asking the number of revolutions per minute it has to complete such that the voltage induced across the conducting material must be equal to what? Must be equal to 1 volt. We know that whenever a conducting bar is revolving, whenever the conducting bar is moving in a B field, there induces an voltage across it. There induces an voltage across it, or I can say there induces an voltage at the ends of what? At the ends of the conducting bar. Understood? Okay. Now how many revolutions per minute it has to make in order to induce a potential of what? A potential of 1 volt across it. So that's what they are asking. right? Okay, okay. So that means we know in order to determine the potential difference between A and B. Okay, so that is equal to what? Just now I have explained here. That is equal to integral A to B E bar dot what? E bar dot dl bar. Here E bar you can replace with what? Minus of V bar cross B bar. So that's what I have told or not? Yes or no? You can use directly this formula. V bar integral A to B minus of V bar cross B bar dot dl bar. So this is the formula you have to use in order to determine the potential. Okay. Okay, so whenever you are trying to determine the potential, VAB is equal to what? Integral A to B minus of, here the velocity is in A phi cap direction cross B field is in negative Z direction. Sorry, B field is in rho direction. Right? Okay, so dot dl bar is along the length of the conducting bar, that is dz az cap. So just we have solved this one. Yes or no? We have solved this one. So what we got? Integral A to B minus of what? V into B A phi cap cross A rho cap is nothing but what? Is nothing but minus AZ cap. Here dz AZ cap. Okay, so what you are going to get here? So minus into minus will become plus integral A to B VB into what? VB into dz. Now here this conducting bar is revolving about the z axis. So you have to consider what? You have to consider the angular velocity. Understood? So here we have represented the expression in terms of linear velocity. Now we have to replace that linear velocity with what? With the angular velocity, and we know the relation between linear velocity and angular velocity, that is nothing but what? V is equal to what? Rho into omega. V is equal to rho into omega. Right? Okay, so just substitute V is equal to rho into omega and do this integration. Okay, so you are going to get this expression. Alok Kumar, is it clear? Tell me here. So we have solved all these things here, right? So we got VAB is equal to this one. VAB is equal to this one, right? Okay, so VAB they have given us 1 volt. So from here we got omega is equal to 1 radian per second. We know that omega is equal to 2 pi f, that is equal to 1. F is equal to what? 1 by 2 pi. So F represents what here? Frequency. Frequency will represent what? The number of revolutions per second. But they have asked number of revolutions per minute. So we have converted this number of revolutions per second into number of revolutions per minute. So that's it. 30 by pi. Right? Alok Kumar, clear? Okay. Rahul Thakur, what you are asking here? Good questions with units, right? RPM, revolutions per minute. Always frequency here. Frequency will give you number of revolutions per second. If you want number of revolutions per minute, so this is the way you have to convert. Understood? Okay. So this question is given for electrical students in GATE. Okay. So I hope this is crystal clear here. See the same concept here, whatever we have followed previously, whatever the problems we have solved previously, based on the same concept they have asked the question. Understood? Okay, just you have to identify what is the direction of velocity and what is the direction of B field. Okay, if you understand these things, okay, then it is going to be very, very simple, right? Okay. Okay, so is there any doubts here further? Is there any further doubts? Alok Kumar, Parasmoon, you are asking something. If I got you as a teacher in IIT JEE, my physics would have been far better than present. Okay. Thank you, dear. Thank you for your compliment. Okay. Okay. Physics is the base here for any subject, okay, whatever we are dealing. So physics is the base, right? Okay. Okay, yeah. So, okay, clear, right? So I hope you have enjoyed the session, right? So with this I am winding up the session, and tomorrow exactly at 4 p.m. Tomorrow exactly at 4 p.m. we are going to start the session here. Okay. Okay. So with this I am winding up the session. So tomorrow exactly at 4 p.m. we are going to meet again and we are going to start the session, right? Okay. So be safe here, stay safe and keep learning. Okay, we'll meet tomorrow. So until then, take care, bye bye. So be safe and keep learning, right? Okay, bye bye, bye bye.